So I like talking so much, I'm going to continue to do so now. So I'm going to start off this. So this is, I guess, a more specific look and follow on from the previous. And we're going to talk about RT security. So this is now, since Thomas has pushed the release, officially part of the DPDK 1711. It's still marked as an experimental API, but it's there and available for everyone to look at and to try out. So what it is RT security is a framework for an API for management and provisioning of security protocol hardware accelerations. Explicitly in this release, we've only been looking at IPSEC, but we've written it in a way that it's generic for managing your security sessions, so it should be scalable to look at a whole range of other security protocols. As we mentioned down at the bottom, like MACsec, PDCP, and etc. So that's future-looking work. In terms of the library itself, it's somewhat unique as it's the first API in DPDK that's multi-device. So you can use the RT Security API both on crypto POLMod drivers and normal net PMDs as well. Let me see, it has a rich capability discovery API, and as I've said, it only targets currently IPSEC. So just in terms of the work, I think it's worth calling out that this was a collaborative work in terms of what has gone into 1711 between Intel, Mellanox, and NXP, that there was a number of RFCs produced in the 1705 sort of time frame, and the people listed there, myself, Hamad, Akil, Radu, Boris, and Avid, we've all worked very closely together to get this upstreamed and into the 1711 release. So thanks for everyone for doing that. So the picture will probably look similar to the previous presentation. So just in terms of the two IPSEC models that are supported today in RT security, we have the inline crypto acceleration, which again it's an IO-based acceleration. There's in general for inline crypto, there's no packet modifications on the hardware, so you're only doing the encryption and decryption. But depending on the implementation, you have different hardware devices have different implementations and different features supported. So things like payload padding is supported on some devices and not others. So the second model of acceleration that RT security supports is the lookaside model. So again, this is where we're giving it to an accelerator. In this case, it's an RT crypto PMD. And we're using the security session in place of the standard crypto op when you're enqueuing and dequeuing the packets from the crypto PMD. In the lookaside model, it has full protocol support. So that includes the encapsulation, decapsulation of the protocol headers and handling the SA state information. It can do anti-replay and sequence number checking, etc. So at that, I'm going to hand over to Boris and let him.
Thanks, Declan. So continuing the presentation about the library. So the API that we suggested, RT security, is protocol agnostic. It creates a session, and then it provides an API to manage that session, to update it and delete it, and query statistics, capabilities, etc. The definition supports many different protocols. We started with the IPSEC as the first implementation, but we intend to provide others in the future. Currently, it includes the acceleration type, which, as Declan mentioned, is either inline lookaside or inline protocol. The definition of the session includes session parameters, such as whether it's tunnel and transport mode, ESP, ingress, egress, etc. The crypto operations are defined using primitives that are available in CryptoDev. So we are reusing a lot of code. And the capabilities allow for dynamic discovery of various hardware features and their support. So here we see an example of the session management API. On the right, we have a configuration of a session. First, there's the action type, which is inline crypto in this case. The protocol is IPSEC, and then there comes the IPSEC-specific configuration options, the SPI, the salt, etc. And finally, there are the crypto parameters, which are called the crypto transform here. So for programming an inline offload, one uses the RTE flow API in combination with the RTE security API. The RTE security API provides a way to configure a session, while the RTE flow describes the packet headers and the patterns of those headers, which are going to be used to identify the session. So in the example here, we are providing an ingress configuration of a security association that's going to use the configuration from the previous slide to provide inline offload. So the packets that's going to be offloaded are going to be IPv4 packets with some ESP header. So those RTE flow patterns would provide the header format and the destination IP and SPI that define the IPsec security association. And then we provide the action, and the action in this case is of the security type, which includes the security session that we've just created. In addition, we need to provide an additional parameter for the steering. Since the security action in RT flow is non-terminating, we need to terminate this session at some queue or pass it on to other rules that were previously defined to do the flow steering. So to summarize, RT security provides an abstraction layer to provision security hardware accelerations. Initially, we are targeting IPsec. It could be used by both Ethernet devices and crypto devices, depending on your model. The combination of RT security with RT flow provides a powerful control plane to define your packet processing pipeline. It is agnostic to applications, which could use different security associations. By defining the RT security in different methods, you could integrate all of those offloads into one application. Finally, the IPsec security gateway sample in DPDK has support for all of these, and there are already 2 PMDs available to provide that, the Intel XGB and NXP's DPA2. Mellanox would provide support in 1802. So try that out and see how you get better performance just by adding a few lines of code. For future work, we intend to provide further enablement, such as further encapsulations of IPsec, LSO and checksum support, which is generally not supported with IPsec since the internal headers are encrypted, and the IPsec inline protocol, which is full IPsec offload, essentially. Further protocols could be supported as well, such as MACsec, PDCP, DTLS, etc. And software equivalent enablement might be of interest to users who would like to enjoy seamless support of such offloads. Any questions? There's a gentleman over there.
Hello? Yeah. For hardware offloading, how it does, to have an impact for the VM migration?
Well, I'm not sure how it relates to the presentation, but in general, when you have some hardware offloading...
For example, the SROVs, right? It gives a challenge for the virtual machine migration. If you VM migrations, right? If you know, offloading some, you know, the stateful security into, you know, into the hardware, but your virtual machine maybe is migrate to the another, you know, server.
Well, generally it depends how your application is structured. If you want to support VM migration in your application, you should support full software fallback of all hardware offloads. So when your VM migrates to another machine where those features aren't supported, you just go through the software fallback path, and it should be seamless.
But how, you know, the states in the hardware can be migrated to the target hardware? That's my question.
Yeah, well, the state is available always in both hardware and software. So you don't offload the state completely. It relies on full software fallback at any stage. So at any stage, you could do the operation either in software, either in hardware, depending on the capabilities of the machine your application is running on.
Questions?
Any other questions?
Okay, actually, you're going to stay up, Boris. You're going to do a separate thing on Mellanox. So if you could do that.